Section 5.2, Evaluating and Graphing Polynomial Functions. So a polynomial is simply a monomial or a sum of monomials. So what's a monomial? Well, a monomial is what you would think of as just a term in a function or an expression. One thing that you need to keep in mind, though, for a polynomial is that the exponents must be whole numbers and the coefficients must be real numbers. Now, we classify polynomials by their degree, and the first two you should be familiar with. The degree is simply the highest exponent. So if it has a degree of 1, it's going to be called a linear function. And you should be familiar with these. The standard form is y equals ax plus b. You might be a little bit more familiar with y equals mx plus b, where the m is the slope of the function. And an example would just be any equation of a line that you're familiar with. A degree of 2 you should also be familiar with from last chapter. If the highest exponent is 2, it's called a quadratic. And again, the standard form, y equals ax squared plus bx plus c. And as long as the highest exponent is 2, then an example of any equation in which the highest exponent is 2 would be a quadratic. For a degree of 3, one way that I think of to remember the type of what a degree 3 polynomial would be is if I have a problem that deals with a length, a width, and a height, and I need to put a label on my answer, that label would be cubic feet, or feet cubed, or inches cubed. And so the type, if it's a degree 3, is a cubic. And again, the standard form, as long as the highest exponent is 3, it's a cubic. And so any example in which the highest exponent is 3 would be your example. The highest exponent of 4. Now, a lot of times people make a mistake and they want to say a quadratic because quad means 4. In fact, it's not, because quadratic is a highest degree of 2. But if you think about the fact that there's 4 quarts in a gallon or 4 quarters in a dollar, hopefully that will help you remember that a degree of 4 is a quartic. And once again, if the highest degree is 4, highest exponent is 4, then that would be your example. If it has a degree of 5 or higher, there isn't really any special names for those. We simply call them an nth degree polynomial. So a sixth degree polynomial or a 10th degree polynomial. One thing that we often forget is that a function could have a degree of 0, though we don't really talk about these because we don't really write an x to the 0. This would be called a constant, and the reason it's constant is if you did have a times x to the 0, well, remember we just learned that x to the 0 is 1, so we would actually have y equals a. And if you realize, then that a is always that constant. Now we need to decide whether the function is a polynomial function, and if it is, we need to write it in standard form and then state its degree, type, and leading coefficient. So is this first example a polynomial? What do you think? Well, hopefully you said no. And the reason you said no is because the exponent is not a whole number. 1/2 is a fraction. Is the second one a polynomial? Well, you might think it's not because it's got that square root of 10, but remember that our constants or our coefficients need to be real numbers, which means they're not going to be imaginary numbers. If that was the square root of -10, it would not be a polynomial. But the square root of 10, we could get a decimal approximation for that and add it to something else. So it is a polynomial. To write it in standard form simply means that you're going to write it with the highest exponent first, and the exponents proceed in descending order. So -8x to the 5th, plus x to the 4th, minus 4x squared, plus the square root of 10. Next we need to state its degree. Well, its degree is simply the highest exponent. So once we have it in standard form, it's that first exponent, which is 5. Based on the degree, we can name its type. In this case, we've got a 5th degree polynomial. And then the leading coefficient, well, when it's in standard form, the leading coefficient is simply that first coefficient, which in this case is -8. When you look at this third example, is that a polynomial? Well, the exponents are whole numbers, and the coefficients are real numbers. So yes, it is a polynomial. To write it in standard form, well, the exponents already start with the highest one and go in descending order, so it's already in standard form. So the degree, well, the degree is the highest exponent, in this case 3. Based on the degree, we list the type, so that would be a cubic. And then the leading coefficient would be the first coefficient, which is, in this case, 1. And now the last example. Is this a polynomial? Well, look closely, and you'll realize that no, it's not. Why isn't it? Well, it's got an exponent of -2, and -2 is not a whole number. Remember, your whole numbers are positive. Your whole numbers are your counting numbers, so they start with 0, 1, 2, 3, and so forth. So make sure you realize that this -2 makes this not a polynomial. Okay, now I want you to try to evaluate this polynomial function when x equals -2. So why don't you go ahead and pause the video for a second and see if you get the same answer that I do. In the meantime, I will continue. So by substituting -2 in, we're just going to plug -2 in for all the x's, and so I'm just rewriting that, putting -2 in parentheses. And then when I evaluate those exponents, -2 to the third would give me a -8. Remember, if you rely on your calculator, to put your numbers in parentheses when you're raising them to a power, because -2 squared is a positive 4. -12 times -2 is going to give me a positive 24. And now when I continue to do the arithmetic and I add these terms together, I realize that f of -2 is 47. And hopefully you got that answer as well. Now we're going to evaluate this using something we called synthetic substitution. And we're also going to be using this process later. So hopefully you'll understand this. So for synthetic substitution, basically what we're doing is we're eliminating all of the x's. And so what we're going to do is, since we're substituting in -2, we're going to put -2 in this little half box on the left. And then we're going to, all of these coefficients, -3, 1, -12, and -5, we're going to list across the top. And now this is the process for synthetic substitution. First you bring down that first term, so the -3 comes down. Then you're going to multiply that -2 times -3. You get positive 6, and you put that underneath the next term. So then you're going to add 1 plus 6 is 7, and you repeat the process. -2 times 7 gives you -14. Adding -14 and -12 gives us -26. Multiplying -2 times -26 is 52. Adding, I get 47. And look at that. I got the same answer as I did with direct substitution. This last value will be the same as when you use direct substitution. Now I'd like you to try this one on your own. First I'd like you to use direct substitution, and then I'd like you to use synthetic substitution. And I'm going to proceed. With direct substitution, we simply substitute in the value of 2. We do the arithmetic, and we get that f of 2 is 17. Now I'd like you to go ahead and try to do it before I do, using synthetic substitution. So you're dividing, or you're substituting, 2 in, and then you would think that you're going to put these coefficients across the top. If we follow this process, bring the 2 down, multiply and get 4, add, we get 3, multiply and get 6, and we add and we get 9. But what's wrong? We're supposed to get 17. Did we make a mistake in our direct substitution or our synthetic substitution? Well, here's the deal with synthetic substitution, is we need to make sure that you have all of the exponents. And if you notice, our original function has an x to the third, and then it jumps to an x to the first. We need to take that into consideration. So our coefficients are actually -2x to the third, positive 2x to the third, plus 0x squared, minus 1x, plus 3. So we need to have that placeholder for every single term. And now if we do our synthetic substitution, we multiply, we still get 4. Now when we add, we're going to get 4. Multiply for 8, and we get 7. Multiply and get 14. And now when we add, we get that 17. So f of 2 is indeed 17. But it really is crucial that you have that placeholder. Now, when we talk about the end behavior of a function, the end behavior of a function's graph is what does the graph do as x approaches positive infinity. So as x gets really large in the positive direction, is the graph going up or down? And then what is the graph doing as x approaches negative infinity, or as x gets really small or infinitely small in the negative direction? And the end behavior of a function is determined by its degree and the sign of the leading coefficient. Let's look, for example, at a quadratic. So let's look at 3x squared. Hopefully you remember from last chapter that this is a parabola, and because of its x squared, and because the 3 is positive, it opens up. So when we talk about, and we use the notation for listing the end behavior, we're trying to find out what happens as x approaches positive infinity. So as x gets really large, as x goes off to the right, what is the function doing? F of x is also going up, so it's approaching positive infinity. As x approaches negative infinity, in other words, the left end of the graph, what is the function doing? Well, the function is going up on that end as well. So this is how you would write the end behavior function. The end behavior of the function. And so what does this mean? Well, the first thing you're going to look at is the sign of the leading coefficient. The sign of the leading coefficient, which in this case is positive, tells you what the right end of the graph does. And so since the leading coefficient is positive, the right end of the graph is going to go up, positive. Then you're going to look at the degree. Since in this case the degree is even, that means the left end is going to match the right end, so it also is going to be going up. So now when I teach this in class, I teach this by doing a little dance called the end behavior dance. And so you get to learn it by stick people doing the dance. So again, it's determined by the sign of the leading coefficient and the degree. So first of all, we're going to realize that when we do this little dance, we're doing the leading coefficient is positive and then negative, and then positive and then negative. So if the degree is even, we're going to say even, both arms are going up. So our right arm is what the right end of the graph is doing. If it's even and negative, then the right end is going to go down, and the left end is also going to go down, because if it's even degree, then both ends of the graph are going to match. If it's odd, then the right end, if it's positive, is going to be going up, but then the left end needs to be opposite. Odd degrees mean the ends go in opposite directions. So again, if the degree is odd, but the leading coefficient is negative, the right side is going to go down, and the left side is going to go up. So my little dance actually looks like this. Even, even, odd, odd. Once more for fun of it. Even, even, odd, odd. And hopefully that helps you remember the end behavior. So how can the end behavior help you graph a function? So we could plot all sorts of points, or we can look at the end behavior. So my leading coefficient is negative, -4, which means that the right end of this graph is going to go down. The degree is 4, which is an even number, which means the left end has to do the same as the right end, so it's also going to go down. So now we could make a little quick t-chart, plug in some negative numbers, plug in some positive numbers, and if we look at the way this is looking, it doesn't necessarily look like the right end should go down. It's starting with -192, and if you notice, all of my y coordinates are getting increasingly large, so you might think that it starts off small and gets large. But we know from our end behavior that that's not the case. So we can plot the points that we know, which really is only those points, but then we can use our end behavior to kind of plot in the rest of it. It starts way down low, and of course we know by our end behavior that it has to end going down. Alright, so that's section 5.2. If you have any questions, please make sure you come in and ask.